Ever wonder if all that dark matter out there is more than just, like, invisible particles?
Hmm.
What if some of it's, like, clumped together into massive structures?
Yeah.
Or even forms, cosmic strings and walls?
Right.
You sent us some research about using gravitational wave detectors,
That's
the
right.
famous LISA mission,
Uh-huh.
to actually hear these cosmic beasts.
It's a really clever approach.
Oh, yeah?
Yeah, most dark matter searches rely on some, hypothetical interaction besides gravity.
Right.
But gravitational waves, those ripples in space-time,
Yeah.
those we can detect.
Okay, so before we get lost in the vastness of space,
Sure.
let's make sure we're all on the same page about gravitational wave detectors.
Okay.
We're talking about those massive laser-based setups like LIGO.
Absolutely. Whether
Okay.
it's LIGO, anchored right here on Earth,
Right.
or
Yeah.
the future LISA mission, gracefully dancing in space,
Yeah.
the core principle is the same. Picture incredibly precise instruments honed to pick up the faintest distortions in space-time itself.
Okay.
These distortions are the fingerprints of massive objects accelerating,
Right.
like ripples emanating from a pebble plunging into a still pond.
So just like that groundbreaking moment when LIGO detected those colliding black holes.
Exactly.
Yeah.
The signals were faint whispers,
Right.
but unmistakably clear, a sure sign of those massive black holes spiraling towards each other
Wow.
in a cosmic dance before their grand finale, a merger.
Yeah.
It was like opening a brand new window into the universe, one that lets us listen to the symphony of gravity itself.
That's incredible. But how do we go from listening to black holes to eavesdropping on dark matter?
Right.
It's not like we can just point a telescope at it and hit record.
That's where the real ingenuity of this research shines through.
Okay.
It zeroes in on the gravitational pull these hypothetical dark matter structures would exert
Right.
on the individual spacecraft that make up a detector like LISA. Imagine LISA as a delicate web,
Okay.
its strands exquisitely sensitive to the cosmic symphony around them.
A cosmic web. Okay, now you've got my full attention. Tell me more.
Picture this. A massive, unseen object.
Okay.
Let's say a clump of dark matter
Right.
cruising through space
Yeah.
near one of LISA's spacecraft, even though we can't see it directly.
Yeah.
Its gravity would tug on that spacecraft
Okay.
ever so slightly.
Okay.
Now, LISA is designed to detect even the most minute shifts in its spacecraft's positions.
I'm starting to see where you're going with this, but how would LISA actually see this gravitational tug?
It all boils down to the Doppler effect.
Okay.
That same phenomenon that makes an ambulance siren change pitch as it races past you.
Right, right.
Except here, instead of sound waves, we're talking about those laser beams LISA uses to measure distances
Okay.
between its spacecraft.
Right.
The dark matter's gravitational pull would ever so slightly stretch or compress the fabric of space-time, causing a tiny but detectable shift in the frequency of those laser beams.
So it's like the dark matter is creating its own Doppler ship symphony as it moves through space.
Yeah.
And LISA is tuned in, ready to hear it.
A cosmic concert indeed.
I like it.
And what's even more remarkable is that the specific characteristics of that Doppler shift,
Right.
how it changes over time, would reveal a treasure trove of information about the dark matter object itself.
Mm.
We're talking of its mass,
Yeah.
its speed, maybe even hints about its shape.
This is already mind-blowing. So did the researchers look at what would happen if LISA encountered, like, different types of dark matter structures?
They did.
Okay.
They explored several scenarios,
Okay.
each with its own unique gravitational fingerprint.
Cool.
First up, let's talk about dark matter clumps.
Dark matter clumps. So we're not talking about, like, evenly distributed particles here,
Right.
but rather these dense pockets of dark matter.
Right.
What would those even look like?
There are actually a few ways dark matter could clump together, even though it primarily interacts through gravity.
Right.
One possibility is primordial black holes, those enigmas born in the universe's earliest moments.
Wow.
Think of them as seeds gathering more and more dark matter around them, like cosmic dust bunnies.
Primordial black holes acting as cosmic dust bunnies. That's quite the visual.
Yeah.
What other mechanisms could create these clumps?
Another intriguing idea is that dark matter might engage in subtle self-interactions
Okay.
that we haven't quite figured out how to detect yet.
Right.
While weak, These interactions could be just enough to encourage dark matter particles to, cozy up to each other,
Right.
forming those clumps.
So we've got ancient black holes or maybe some hidden force drawing these dark matter particles together.
Right.
It's like the universe is playing a cosmic game of hide and seek with us.
Yeah.
But let's get down to business. Could LISA actually detect one of these clumps?
Well, according to the research, LISA could potentially pick up on a clump with a mass equivalent to a staggering 10 billion tons.
10 billion tons.
It's about the same mass as a hefty asteroid.
Wow.
A celestial rock, several football fields in diameter, all made of dark matter.
A dark matter asteroid lurking out there in the void. That's one way to make an entrance.
Yeah.
But how close would this clump have to be for LISA to notice it?
That's the million-dollar question.
Right.
Or perhaps I should say the billion-ton question. Even for a clump that massive, it would need to pass within a few 100,000 kilometers of LISA to create a strong enough signal for us to detect.
Yeah.
Based on our current understanding of dark matter's distribution, such an event might only grace us with its presence once every few centuries.
Centuries. That's quite a long constant intermission. Talk about delayed gratification.
Yeah.
So while LISA might have the years for it, it sounds like we're going to have to be incredibly patient.
Yeah.
If not downright lucky.
Yeah.
To catch a dark matter clump in the act.
Patience is indeed a virtue in astronomy.
Well said, well said.
But don't lose hope just yet.
Okay.
Remember how I mentioned those low-frequency gravitational waves?
Yeah.
Well, enhancing LISA's sensitivity to those lower frequencies could significantly shorten that waiting time.
Okay.
Potentially bringing those whispers from the dark side of the cosmos within earshot.
Insurance.
Much sooner.
That's reassuring. So dark matter clumps were just the opening act in this cosmic symphony of possibilities.
Right.
Up next, we have cosmic strings, which sound even wilder.
Yeah.
Give it to me straight.
Yeah.
What are we talking about here?
Okay.
Are these like the strings on a cosmic guitar?
Well, imagine this. Incredibly thin,
Yeah.
yet almost unimaginably long.
Yeah.
Defects in the very fabric of space-time.
Defects.
If space-time is the canvas of the cosmos, then cosmic strings are like those tiny, almost invisible imperfections woven into its very essence.
So not quite guitar strings then, more like wrinkles or snags.
Yeah, like...
In space-time itself, how do those even happen?
Picture this. The universe is young, a hot, dense soup of energy undergoing a period of rapid expansion, known as inflation. As this energetic soup cools down, different regions of space might settle into different states, kind of like cracks forming in ice as it freezes.
Yeah.
These cracks are what we call cosmic strings.
Okay, I think I'm starting to wrap my head around this.
Yeah.
But if these cosmic strings are so incredibly thin, wouldn't their gravitational pull be negligible?
It could be, yeah.
Like trying to hear a whisper in a hurricane.
Right.
Could LISA even dream of detecting something so faint?
You're right. The gravitational pull of a single stationary cosmic string would be far too weak for LISA to pick up.
Right.
But here's where it gets really exciting.
Okay.
The research suggests that instead of individual strings just hanging out in space, we should be on the lookout for networks of these strings, all intertwined and interacting with each other.
Networks of cosmic strings. Now we're talking. All right. So it's like a giant interconnected web of these wrinkles stretching across the universe.
Yeah.
That sounds significantly more substantial than a lone string just like vibing in the void.
You've got it.
Okay.
These networks could be far more massive and dynamic than a single string, potentially producing a much stronger gravitational wave signal.
Okay.
Particularly in those low frequency ranges where LISA is particularly astute.
Right.
It's like the difference between trying to hear a solo violin in a crowded room versus a full orchestra playing fortissimo.
Okay, so these cosmic string networks, if they exist, would be a much more enticing target for LISA than a lone string just hanging out in space.
Right.
And I'm guessing this is where things start to get really interesting, right?
You're catching on quickly. Some theories propose that these networks of cosmic strings could actually be a significant component of dark matter itself.
Hold on. Dark matter could be made of these cosmic string networks.
Potentially, yeah.
So instead of thinking of dark matter as particles, it could be these massive interconnected wrinkles in the fabric of space-time.
In a possibility.
That's a seriously wild concept.
Precisely. Now, I have to emphasize that this is still very much a theoretical idea.
Right.
But it's a fascinating one, wouldn't you say?
Oh, absolutely.
And if LISO were to detect gravitational waves emanating from such a network, it would be a monumental breakthrough in our understanding of both dark matter and the fundamental nature of the universe. And believe it or not, that's not all. This research didn't stop at cosmic strings.
Really?
They dove even deeper into the theoretical rabbit hole, exploring another, even more bizarre type of dark matter structure: domain walls.
Domain walls. You're really pushing the boundaries of my imagination here.
Right.
Cosmic strings were wild enough,
Yeah.
but now we're talking about walls.
Yeah.
What exactly are we dealing with here?
So if cosmic strings are wrinkles in space-time,
Okay.
then imagine domain walls as, like, entire sheets.
Two-dimensional boundaries separating different regions of the universe.
Okay.
Imagine the universe as a giant patchwork quilt.
Right.
And these domain walls are the seams holding everything together.
Okay, I'm trying to visualize this. We're talking about massive, invisible walls slicing through space.
Yeah.
What would even create these cosmic walls?
Similar to their string-like counterparts.
Yeah.
Domain walls are thought to be relics from the universe's infancy.
Okay.
Potentially forged during phase transitions as the universe cooled down.
Okay.
Imagine water transitioning from a liquid to ice.
Right.
As it freezes, different regions of water molecules align themselves in different ways, creating boundaries between them.
Right.
These boundaries are kind of analogous to what we're talking about with domain walls.
So you're saying these domain walls are like cosmic versions of those boundaries.
Yeah.
But on a scale that's, like, almost impossible to grasp.
Exactly.
Wow. Okay. So how do you think LISO would go about detecting a domain wall?
It's not like you can just bump into one and yell, "Eureka!"
That's a great point. It's not like we're talking about a cosmic game of Marco Polo here.
Right, exactly. So how would LISA even know a domain wall was nearby?
This is where things get really fascinating. A domain wall's gravitational field.
Yeah?
It's constant.
Okay.
It doesn't weaken with distance like the gravity of a clump or string.
Right.
So instead of feeling a passing tug,
Right.
LISA would actually be stretched by a passing domain wall.
Wait, stretched? You're saying the spacecraft themselves would be physically pulled apart. That's a bit more intense than I was picturing.
It would be a very, very subtle stretch.
Okay.
But it's something that LISA would theoretically be able to detect.
Would LISA survive such an encounter?
Theoretically, yes. LISA is engineered to be incredibly flexible, built to withstand the stresses of space travel, including the sun's constant gravitational pull,
Right.
the stretching caused by a passing domain wall, while definitely noticeable, wouldn't necessarily spell disaster for the spacecraft.
Okay.
Imagine it more as a subtle yet measurable distortion.
Okay.
Like a cosmic yoga session.
A cosmic yoga session for a space probe. That's one way to put it. So how often do the researchers think LISA might find itself in this cosmic stretch?
And here comes the truly mind-blowing part. Based on their calculations, a domain wall encounter could be far more frequent than stumbling upon a dark matter clump or even a cosmic string network.
Really?
We're talking about a potential encounter every few years, not centuries.
Every few years. That's like practically tomorrow in cosmic terms.
It's very frequent on cosmological timescales.
So are you telling me that these domain walls, which sound like something straight out of science fiction, might actually be the easiest type of dark matter structure for LISA to detect?
It's definitely a real possibility.
Wow.
Of course, this prediction hinges on a number of assumptions, such as the specific properties of these domain walls and how they're distributed throughout the universe.
Right.
But if it proves true, it could change our understanding of the cosmos as we know it.
It always comes back to assumptions, doesn't it?
Yeah.
It seems like every time we uncover a new layer of the universe, we end up with even more questions. So we've covered these three potential ways dark matter could be hiding out in massive structures, clumps, cosmic strings, and now domain walls. Did the research explore any other possibilities?
They did.
Okay.
They actually considered one more fascinating scenario, which takes a different approach.
Okay.
Imagine, instead of hunting for distinct objects, we tune in to the subtle, continuous hum of gravitational waves produced by the overall density fluctuations within dark matter itself.
So instead of looking for the big, splashy events, they're trying to eavesdrop on the quiet background noise of dark matter.
Precisely.
That's like trying to hear the soft whisper of the wind through a forest instead of a roaring waterfall.
It is. It's a much more subtle signal, for sure. But it could tell us profound things about the overall structure and behavior of dark matter.
I love that analogy. It
Yeah.
really puts things into perspective. So were the researchers able to make any predictions about how loud this dark matter whisper might be?
Whoa!
Would LISA even have a chance of picking it up?
Unfortunately, their findings weren't quite as optimistic on that front.
Oh,
Their calculations suggest these density fluctuations are probably far too weak for LISA to detect with its current level of sensitivity.
so we'll need to wait for even more advanced gravitational wave detectors
Most likely, yes.
to hear these whispers from the dark side.
Potentially, yes.
Yeah.
However, there was one very intriguing exception they found.
Oh,
If these dark matter fluctuations are incredibly large and dense,
yeah?
much like those clumps we discussed earlier,
Okay.
then LISA might just stand a chance of detecting them.
Okay.
It's like those clumps hold the potential to amplify the signal, making those whispers a bit easier to pick out from the cosmic background noise.
It all circles back to those clumps, doesn't it?
It seems that way.
It's like no matter where we turn in our quest to understand dark matter, those massive structures keep popping up as a potential key.
It's true. This research really highlights the incredible potential of gravitational wave detectors.
Yeah.
They're not just for studying black holes and neutron stars anymore. They could become our primary tool for finally peering into the heart of dark matter and unraveling its secrets.
That's a truly exciting thought, and it makes you wonder, what other secrets is the universe hiding, just waiting for us to develop the tools to listen?
It's incredible to think that we're on the cusp of potentially hearing the universe's hidden symphony,
Yeah.
with dark matter as the conductor. It's like we're standing at the edge of a vast, unexplored ocean,
Right.
and we've just, dipped our toes in the water.
That's a beautiful way to put it. And just like exploring a vast ocean,
Yeah.
unraveling the mysteries of dark matter requires patience,
Right.
ingenuity.
And a healthy dose of curiosity. It's a reminder that science is a journey, not a destination.
And what a journey it's been so far.
Right.
We've gone from these faint whispers of gravity
Yeah.
to imagining cosmic strings stretching across the universe
Right.
and domain walls separating like different realities.
It's pretty mind-boggling when you think about it.
It's enough to make your head spin.
Yeah.
And the most exciting part is that we're really just getting started.
We are.
As our instruments become more sensitive,
Right.
as we develop new techniques for analyzing these faint signals,
Yeah.
who knows what other wonders we'll uncover.
Who knows? That's what's so exciting about it.
That's what I find so inspiring about this kind of research.
Yeah.
It's a constant reminder
Mm.
that there's so much more out there
Absolutely.
than we can even imagine
Yeah.
waiting to be discovered.
Yeah.
But for now,
Right.
I think we've given our listeners plenty to ponder.
We have.
Any final thoughts you'd like to leave them with?
Sure. If there's one thing I hope listeners take away from this deep dive,
Yeah,
it's that the universe is full of surprises.
it is.
Dark matter, this invisible force that shapes the cosmos,
Right.
is just one example of how much we still don't know.
That's true.
So keep asking questions,
Yeah,
keep exploring,
right.
and never lose your sense of wonder.
Beautifully said. And who knows?
Yeah.
Maybe one day, one of our listeners will be the one to finally crack the code of dark matter
That would be amazing.
and rewrite our understanding of the universe.
Yeah.
Until then,
Yes.
keep looking up at the stars and remember,
Yeah.
there's a whole lot more out there than meets the eye.
Absolutely.